Okay, so let's begin with what a supernova is, because I will talk about supernova, so I hope we all know what supernova is. So a supernova is the explosive death of a star. When a star is born in isolation with more than around 8 solar masses, it will burn enough heavy elements to produce an iron core. So it will start with hydrogen to helium, helium to carbon, oxygen, and so on, until the core is made of iron. And the reaction to burn iron doesn't release energy, but consumes energy. So the radiation pressure and the gravitational pressure cannot sustain each other anymore, and the star collapses into itself. And this collapse produces what we call a core collapse supernova. Yes. A core collapse supernova produces a compact object or a compact remnant that can be either a neutron star or a black hole. Now, if the star is born with a companion and is less massive, it will not be able to burn as heavy elements as a massive star can. But if the companion is able to transfer enough mass during the last stages of the evolution of this star, this less massive star, then it can exceed the Chandrasekhar mass limit and then explode in a thermonuclear explosion. So in this case, a low mass star will burn hydrogen into helium, carbon, oxygen, and then become a white dwarf. And then at this stage, it will receive mass. So if the companion is another white dwarf, then we believe that a merger is produced to produce explosion. But if the companion is a sequence star, then the mass transfer will be produced by winds. So this is all I will talk about thermonuclear supernova. I will not care about them anymore. Although if you do cosmology, you probably care. But me, in this case, I will just stop here with this sort. And I will only focus on core collapse events. Why are supernova interesting? Or why I care about them? Or why? Yeah. I think they are very relevant in many aspects. So one of the aspects that are relevant is that because they produce many of the heavy elements that we know. They also have a huge impact on their environment. When a star explodes, it releases all the elements that it has produced into the environment. So it has effects into also the galactic evolution. And they can trigger events of stellar formation and so on. So they enrich their medium. They also are important for stellar evolution because they are the end of the life of a star. Because they are very, very bright, we see them in very far away galaxies. They also help us to understand the shape of our universe. Because they produce core collapse supernova produce compact objects, they can help us understand what we call the stellar graveyard, which is the number of black holes and neutron stars that we know. And if all of this doesn't convince you, then it's also a great name if you're like creating a movie or something, you just can call your movie supernova. Okay, there are many types of supernova. So we classify them. And we classify them empirically based on the presence or absence of certain lines in the spectra. So here, let's see if I can make this work. Yes. Here in the mid panel, you can see examples of different spectra of different types of supernova. So if there is hydrogen in the spectra, we classify as type 2. We say it's hydrogen-rich. And I hope this gives a hint of what I will be talking after this slide. So hydrogen-rich events have hydrogen in the spectrum. If there is not hydrogen but helium, then we classify as type 1b. And if there is no hydrogen, no helium, then we say it's a 1c. And there are these transitional events that show hydrogen early on that then disappears. Each type also have some sort of characteristic light probes, and we have different subclasses based on light probe properties, also on spectral properties. For example, among type 2s, we can subclassify events of type 2p if they show a plateau. So if you see here in the left-hand side, I guess, or right-hand side, for you it will be right. Here you can see a typical type 2p light probe shows this plateau. And because of this plateau, we call it type 2p. If the light probe declines linearly after peak, we classify them as type 2L. And of course, if the light probe is very, very luminous, we classify them as superluminous events. There is also some spectral subclasses. In particular, it will be important to remember that there are some events that are called type 2N. And type 2N are events that show hydrogen, but instead of having this nice P-Cygni profile, show a narrow line in the spectrum. Classification is important because it allows us to infer things about the progenitors. So we want to know what are the stars that explode. So if we think about hydrogen-rich events, we assume that if we see hydrogen in the shecta of the supernova, then there was hydrogen in the outer envelopes of the progenitor star, the star that exploding. If we don't see this hydrogen, then the progenitor star must have been stripped of the outer envelopes. And if we don't even see helium, then this stripping process must have been higher. So we have a sequence. If we consider the star at the end of its evolution as these sorts of schematic onion layers with the different elements. So there is a sequence of stripping that happens as we move in the different classes. And this sequence is a mass sequence. And this is an increasing mass sequence to the bottom, let's say. Massive stars, all of them lose material. But the most massive a star is, the more violent the process of mass loss. So a star has to be very massive to be able to strip a lot of its outer envelope because it needs the very, very high winds. It has to have a high mass loss rate. So we believe that like strip envelope supernova arise from progenitors that are more massive than hydrogen-rich events. Light curves can also tell us something about the progenitors. So in this case, we have type 2, supernova type 2 light curves. This is the largest sample to this date. So in 2014, Anderson et al. Studied the largest sample of type 2 supernova to that date. And as I said before, there are events that show the plateau and there are events that don't show the plateau. So we believe that type 2 supernova are also powered by hydrogen recombination. So the supernova explode, there is a shock breakout, some cooling, some radioactivity happening that produces the first peak. And then during this whole process, hydrogen was excited and the hydrogen recombines. And this recombination gives a steady infuse of energy. And so we see this plateau. But type 2L also show hydrogen. So what we believe is that there is less hydrogen to be recombined to power this plateau. So there will be a sequence of events that show the plateau that have retained more hydrogen, to events that don't show the plateau and decline linearly that have retained less hydrogen. Still enough, so we see during the whole evolution of the supernova, but less than the ones that show the plateau. This also would imply, if this is true, implies a continuum in a mass sequence for these events within the events that show hydrogen. And this has been supported by the study of the features of these light curves that also show a continuum within themselves. So the features of these light curves show a continuum, so we can support a continuum in the progenitor mass of these events. So why do I care about superluminous supernova? One, if we see this graph presented but adapted from the work of Perli et al. In 2020, where the study rates of the number of observed events, we can see that most of the observed events are supernova 1A. These are the thermonuclear explosion that I mentioned before. Then we have some fraction of core collapse. And among the core collapse, hydrogen-rich are the most abundant. However, superluminous supernova are the least abundant within the events that show hydrogen. So these are the ones that we understand the least. So we really don't know a lot about these events. And we understand a lot about the normal type 2s. I show you the light curve and I show you our interpretation for the progenitors and everything. But we don't know why there are some events that show light curves are so luminous. So what is the connection between their luminosity and the progenitor? What is the physics that are going on there? Luckily, we have many surveys that scan the sky and discover transients. And so this is a graph obtained from the Transient Name Server, which is the official IAU place to go look for transients. And these are some surveys that contributed to last year's discovery of transients. And so this is the number of transients discovered only last year by all these surveys. And I'm sure you know some of these surveys. And this is a similar plot, but taking into account the number of classified events since 2016. So in 10 years, we were able to classify only these transients out of the many that are discovered every year. So this is because we lack spectroscopic resources. So we are very good at detecting transients because we have a lot of photometric resources. We can produce light curves, but it's difficult to get spectra because the classification is spectral based. So it's difficult to get a lot of classification. Luckily here, there are people that are contributing a lot. So Ismael, Fred, and some other people here discover many transients. So they actually contributed a lot during the pandemic at the discovery of transients. And they also have been steadily classifying transients, which is very great work. We appreciate them for it. Because of the efforts that people have made in classifying events, now we have enough classified type 2 superluminous supernova that we can perform a large sample analysis. The ultimate goal of our analysis is to try to understand the explosion and the progenitors and the physics that are involved. So why are these events more luminous than other events? Is it because the progenitor explodes with a higher intrinsic explosion energy? Is there a central engine contributing to the energy budget? So supernova produce compact objects. If this compact object is a magnetar is a highly magnetized neutron star, the spin down can help power the light bulb. Or if there is a central black hole, there is fallback into this central black hole, this process can also power the light bulb. And the other thing that can produce extra energy is an interaction with circumstellar material. As I said before, stars lose mass during their life, and this mass it remains in the medium. And so if the supernova explodes and the ejecta of the supernova collides with this material that was expelled by the progenitor star, this interaction can also produce energy that contributes to the energy budget of the light curve. Still, even though this is our ultimate goal, intermediate goal is to be able to photometrically distinguish these events from other events. This is important because, as I said before, we don't have a lot of spectroscopic resources, and we are at the almost at the beginning of the Vera Rubin Observatory Legacy Survey of Space and Time, LSST, that will discover millions of transients, and we will only have light curves, and so we want to tell them apart only based on the light curves. So we have a sample, and this sample was collected within the Zwicky Transient Facility Survey, CTF. So we have 107 superluminous supernova type 2. So we included all the events within CTF that were superluminous, and they had hydrogen. Some, let's say, important points regarding the selection criteria is that we only consider events that have hydrogen, and we didn't care if these hydrogen features were narrow or not. If a hydrogen feature is narrow, we know there is circumstellar material interaction. Narrow features are produced by this interaction. But if the narrow features are lacking, then we don't really know what's happening. So our idea was that if there is a key difference between the light curves of things that show narrow lines and those that don't, they will separate organically in the sample. And the other thing is that we consider superluminous supernova anything that is brighter than -20th magnitude in any of the CTF bands. These are G, R, and I. Typically, well, The threshold, the magnitude threshold to characterize something as superluminous is very arbitrary. We have adopted -20 because it's what in the literature. Usually the threshold is applied to bluer bands. However, if you consider something superluminous in a G band, let's say, and because it reaches, if we don't consider something superluminous in the G band because it doesn't reach this threshold, then you are missing out on highly reddened events. So something can be highly reddened, and you can see in the I band that it's superluminous, and you miss it because you are only focusing in the bluer bands. So we consider the three of them. And we put some constraint on the time of the observations just to put some constraint on the project because events keep appearing and we don't want to continue forever with the project. We need to have a stop. We include the sample presented by Kang et al. In 2022 as a comparison sample. They studied 11 type 2 superluminous supernova that didn't have narrow lines in the spectra. So I specifically selected anything that didn't have narrow lines. So again, when comparing with his sample, we are trying to see if there is some trend that we are not seeing within our sample. So this is the redshift distribution of our sample. So you can see it's not high redshift, but it's on the high end, let's say. This is our sample, and in cyan here is the redshift distribution of the sample of Kang. And we have 11 contaminants that I will discuss at the end. So we do some analysis, we measure some parameters. Of course, we measure the peak absolute magnitude, which is the one parameter classifying this as superluminous. Throughout the whole presentation, G band will be presented in green, R band in red, and I band in yellow, and this light green will be the sample of Kang. So here is what I said before. There are events that in the G band are not considered superluminous, but then when you observe redder bands, you can see that they are superluminous. And we also measure some time scales. We measure the rise time and the decline time, and the rise time is the time from explosion to peak, and the decline time is the time it takes to decline after peak. However, it's very difficult to measure the explosion, to pinpoint the explosion epoch accurately. So instead, we measure this rise and decline time based on difference in flux. And in particular, we consider the definition presented in Chen et al. 2023, where they consider flux difference of 10% of 1/E, which roughly translates in difference of magnitude of 2.5 and 1.09. So the rise time in this case, let's say the rise time 10% would be in the rise of the light curve, whatever point in time that the photometric point is 2.5 magnitudes away from the peak. So this elapsed time will be our rise time. And so here we have the distribution rise time 10%, 1/E, decline time over E, and decline time 10%. Of course, 10% for the rise, and for the decline, we have the lower amount of events because there are not many events that last that long or have such fluctuations in flux. But we have more in the 1/E. And we try to see if we see any trends. So we try to study correlation between the peak absolute magnitude and the time scales, and we don't see any. You could say, oh, here you have a rise 10% versus peak absolute magnitude in the R band, you have some correlation. But this correlation, we don't believe because it's driven by this low number of points. And we don't see any other correlation anywhere else. And we also don't see groups of points forming. Everything is just sort of spread around. We do see a correlation between the rise time and the decline time. So events that rise faster also decline faster, except in the R band, there are these outliers that are making the correlation very weak. So these events here are super interesting because they don't follow the trends. But usually, yes, things that rise fast, decline fast, things that rise slow will decline slow. Using the 3-band GRI, we can obtain the SED and we can create a pseudo-volumetric light curve. And from this, we can estimate the total radiative energy of our sample. So for a normal supernova, we usually say that the normal energy, let's say, or energy budget is 1 foe. A normal explosion energy is 1 foe, is 10 to the 51 ergs. So 10 to the 51 ergs is here. So everything below this line could sort of be explained by normal models. Nowadays, normal models, normal explosion models also includes interaction because they consider that the star lost mass during its life. But these two events here, one of our sample and one of the Kanga's sample, are way more energetic. So these for sure need some other mechanism to explain the light curves. And when we take a close look into the sample, we see there is a lot of variety. So as we said before, energy-wise, things could be explained with CSM. So can CSM explain all of these? So there are events that show multiple peaks. And so if you see multiple peaks, you can say, okay, I have different layers of CSM. So my supernova explodes, my ejecta expands, as it hits the first CSM layer, it produces the first bump, then it continues to expand and it hits a second layer of CSM and then another bump and so on. And these bumps, you can, I mean, you are free to imagine whatever amount of bumps, whatever amount of CSM layers as you want. Things that are slow, that decline very slow, things that rise very slow can also be explained by CSM. If you have CSM that is heated and this heating is produced slowly because the CSM is very dense, for example, then you will have a very slow rising light curve. The same for something that declines slowly. So now you have your CSM and the CSM is heated and then it cools off slowly. And so your light curve declines very slowly. So the thing with CSM is that you can really tailor to fit whatever you want. And in general, most supernova models are like that, except there are hydrodynamical models that have some sort of way to break the degeneracy that exists when modeling light curves. So usually it's good for models to include information from a spectra, for example. So you include information about the ejecta velocity that you can measure from the spectra. So otherwise, you are sort of really free to say what you want, because even if I find one model that really fits my light curve, I can find many others that also do. And for example, these events like this here, that is very luminous and very broad, have been explained with CSM, with fallback equation, with magnetron. So there are examples of events like that explained with different models. And all the models fit because there is a degeneracy in the models. So as I said before, we want to understand the powering mechanism, but we also want to try to classify events based solely on the light curve. So we compare first here in the top panel with events that have narrow lines. So in red is our superluminous supernova sample. In magenta is the one of Kanga's et al. And in gray is the supernova type 2N sample from Nihon et al. In 2020. And we compare with that sample particularly because those events, the type 2N, we know are powered by CSM. So if we zoom in, we don't really see a lot of difference, let's say 100 days around peak. The main difference is the peak luminosity. But at this time, we don't really see a difference between our superluminous supernova and the type 2N. However, if we look for longer times, type 2Ns usually decline faster than superluminous supernova. There are some recent works about this, but it's like very niche. But if you're interested, I could say more about this. We also compare to the type 1 superluminous supernova. And this is because when we have light curves, we will know something is superluminous because it's a magnitude threshold for the peak, but we will not know from the light curve whether we have hydrogen or not. So here in green is our type 2 sample, and in gray is this type 1 sample presented by Senator in 2023. And again, if we zoom in, we don't really see a difference. But when we see the whole picture, we see some things that are different. One thing that we see different is that if we measure the color, the G minus R color at peak, and we compare with the peak absolute magnitude in the G band, in general, type 1 superluminous supernova are rather bluer and brighter. So in gray is the type 1. So we see that type 1s are slightly bluer and slightly brighter. So for the the brightest events, we could sort of say, okay, if it is really, really bright, maybe it's a type 1. But otherwise, or if it is really, really blue, maybe it's a type 1. But otherwise, we don't know what it is. We also compare G peak absolute magnitude versus timescales. And what we can see is that there is not a lot of difference between the type 1s in gray and the type 2s in green in the rise time, but there is a difference in the decline time. So usually type 2s decline very, very slowly. So you could say, okay, if something is, the light curve lasts more than 100 days and it's still there, then maybe it's a type 2. And as I said before, we have contaminants. So these are the 11 contaminants that we have in our sample. So these are events that were originally classified as type 2 superluminous supernova. And actually, if you see up to 100 days and you see the spectra, then you don't doubt anything. But then you take a closer look and then you start doubting, especially if you take a second spectrum or a third spectrum. And so these things, the more purple ones, are Asian. And the more greenish ones are TDs. Asian is active galactic nuclei, TDs, tidal disruption event, which are produced when a star goes very close to a black hole and then is disrupted by tidal forces. So the only way that we had to distinguish these events from our superluminous sample was to have further spectra. So it's very complicated to really disentangle this very, very luminous event because they are very luminous and they are sort of also very similar light curve-wise. And there is a funny object that I like. So this was classified on TNS, I said before, the transient name server. Originally, it was classified as other. Then someone got the second spectrum and said, oh, no, okay, it's type 2 because there is hydrogen. But then someone said, no, it really is an Asian, it's a Cipher-1, it's a Cipher-1 galaxy, and they put it here because the light curve is similar to other Asian. And then there was a neutrino detection associated to it. And so someone said, oh, no, if there is a neutrino detection, then there is a black hole involved or something like that, and it must be a TDE. And so then someone else says, no, neutrinos are associated to supernova, so it's actually a superluminous supernova. So you see, it's really not trivial to discard contaminants in these cases. And so as I said before, we want to classify because the LSST will produce many light curves and so on. So I simulated how we would see some of our light curves in the LSST. So there is LSST had this observation simulator. And so you can decide on a region of the sky and see how the observations will be there. So what I did was to see where the CTF footprint and the LSST footprint overlap. CTF is north Chi and LSST is south Chi, but they still have some overlap. So for the events that are in this footprint overlap, I simulated the LSST light curves. And so here in circles, in dim circles, you see the CTF observations, and in stars is the LSST observation. And I only did this for GR and I bands. So with the off simulator, with the cadence that was available at this time, I found that you can miss up to 80% of superluminous supernova. And when I say you miss up to 80% of superluminous supernova, you don't miss the event per se, but if you miss the peak, you cannot know it is superluminous. So you will probably classify it as supernova, but you will never know it was superluminous. Of course, you will lose less events in the redder bands. So maybe, but this is also how LSST is designed. So maybe other redder bands will become important at this time. But since the key point here is to spot the peak, then we have to be careful. There is another caveat to this analysis, that this analysis is made for the redshift distributions that I show at the very beginning, which I say, okay, they're a bit far away, but they are not that far away. And the other thing that LSST will have is that it can reach very high depths. So it can observe very dim events. So if you can go very deep, then you can observe very far away. And so if you observe very, very far away, then there are some time dilation effects that will make your light curve less worse sample, let's say. So for time dilation, your cadence will become better. And so you will have better sample light curves for things that are very, very far away. So yeah, this is a caveat to this. So this seems very bad, but it's not as bad if you consider the fainter events, but it's a bit bad if you consider brighter events. So it's really important to have other surveys complementary to LSST to fill in the light curves. So with this, I conclude. I don't even know how long I took, but the conclusions are here. So if we want to know what are the physics behind this, we need more models. Particularly, we need models that include spectral features or other features that allow us to have a smoking gun telling us, okay, now this is really what's happening. We need more data, always. So, especially we need spectral data. And when LSST is here, we will need to be able to coordinate ourselves. We need to coordinate our observational resources to not step on each other, and also to be able to have the more comprehensive data set that we can, so we can really classify things accurately. Otherwise, we will have a lot of superluminous supernova that were HCNs or TDs and so on, and we will have no way to tell them apart. So yeah, that's it. Thank you.
Okay, thank you, Priscilla, for the nice talk. Any questions for her?
Thank you, Priscilla. On slide 24, I have a question.
Yes.
Yeah, on the plot on the right, is the contribution from the host taken into account?
Yes, so because this is CTF photometry, differential photometry, the host is subtracted when you consider the reference image.
Okay.
Yeah.
The same related question. But what about the extinction correction rather than?
Yes, in this case, we don't consider any host extinction. Still, let me see if I have. Okay, I don't have it here, but when we study the colors, I thought I put it here. When we study the colors, we don't see many things are highly reddened. So even if we don't consider host extinction, we don't think there are things are very extincted because the colors are all somewhat consistent among themselves. So we analyze the G minus R colors.
Okay.
Thank you, Priscilla. Very interesting. I have a more general question. As you said, nowadays we are identifying several transients and following up with photometry, with photometers at the end. We are not even able nowadays to follow up with spectroscopy, all of them. And now with the LSST, situation will be much worse. So my question is, what will be the situation, and what do you propose to take the advantage of the whole set of data LSST will provide? And then, in terms of the spectral band, do you think that we should focus our resources in the optical, or infrared is also something that we should not discard to exploit this new set of data that will be coming?
Yes, so I'm here with not very optimistic because of this particular sort of transients that are not very well understood. So superluminous supernova are not very well understood. But there are other supernovae that are better understood and that you can classify from the light curve. So for example, type 2P supernova, they are easily classified by the light curve because you see a plateau. Type 1A supernova are also easily classified by the light curve. And there is a lot of effort put in developing light curve classifiers. So if you go check, there is a full forest of light curve classifiers. Some of them performing better than others. However, there are still these strange events that you will miss if you don't have a spectroscopy. So to me, the best approach is coordination. So if you have gaps in the light curve that you can easily fill with other surveys, and then you can easily say it's a type 1A supernova, then you don't waste your efforts on that. Well, maybe if people doing cosmology, they will want, but if you don't do cosmology, then you don't use a spectral time for that. And then you only use a spectroscopic time, let's say, for the weirdos, the ones that even when you fill in the light curve seems very strange. Still, a lot of surveys will not reach the depth of LSST. So even though it will be easier to try to get spectra from things that are brighter, I personally think that maybe we will get the most by trying to invest more time in going for the bit fainter things to try to discover things that we have never seen before. And the other thing is with the infrared spectroscopy, I think there is a lot to learn. Well, first, there is not a lot of characterization of supernova in the infrared, but all the classification that we have is on the optical. Still, if things are very far away, everything will be redshifted. So we will not be able to know what is the classification in the optical. So if we don't get an infrared spectrum, we have no idea how to classify it because our classification scheme is all in the optical. And I don't know if I answer all your questions.
Yeah, absolutely, absolutely. Thank you.
Yeah, thank you for the presentation, global overview. And I was wondering about the mechanisms of powering those. So type 2 is mostly CSM. So you see hydrogen in the spectra, or so does that mean that it's dominated by CSM or decay or?
No, seeing hydrogen in the spectra doesn't mean it's dominated by CSM. It means that there is hydrogen in the in the spectra. Now, if this hydrogen feature is narrow, then you can assume that you have electron scattering that is producing this narrow profile. So this is why narrow line is evidence of CSM. Still, the models of normal type 2, not even superluminous, usually fail to fit the peak of normal type 2 supernova. So most people, what they have done is include a thin layer of CSM so they can boost the luminosity of the peak. And with these thin layers, they have been able to reproduce the peaks of even normal type 2 supernova better. So this is why we more and more think that CSM is a predominant mechanism. But yeah, having hydrogen doesn't necessarily mean CSM. And actually CSM was very much ignored for a long time, even when we had narrow supernova with narrow lines. It's just that other models were developed, and then one that was very popular and one that is very popular among type 1 superluminous supernova is the magnetar model. The one problem with the magnetar model is that you can fit anything with magnetar. Of course, you can also fit anything with CSM. So it's really how much you trust the tweaking of your parameters if you don't have anything else to say. So I don't do models, and I usually just like to stick to the observational characterization of things. Then I can be free to say, okay, I don't do this. But I feel like a good approach is always to try to try different models and to try to see out of these different models, what are the physical parameters that you get? Like, what is your mass loss rate from your model? What is your nickel mass from your model? so many parameters and to try to see which of these parameters that you get make more sense. So if you are getting a mass loss rate of, I don't know, 1,000 solar masses per year, I don't know, something like crazy things, then you will discard that model and you will say, okay, I favor here magnetar because the physical parameters of the CSM model are crazy.
But so far, there is no observational evidence that type 1 and type 2 have different powering engines.
No. The only thing is when you have a GRB associated to a 1C supernova, as the only smoking gun, but otherwise no.
Okay, but so for type 2 and type 1, it's still the same possibilities, CSM, magnetar.
Yes.
And okay,
Yes.
so and the fact that they are bluer, we don't know.
We don't know.
Okay.
They can be somewhat higher, somewhat more energetic or something like that, but there is no smoking gun. No. There are some things that you can, if you have very dedicated spectroscopic sequence, for example, something that would be a smoking gun is getting a spectrum, I don't know, 0.5 days after explosion. And then because of normal models, there you should see flash spectroscopic features. So if you see flash spectroscopy, then you have CSM. So these features that arise from the Schecter heating, the Schecter being very hot, heating the CSM and so on, it produces narrow features for very short amount of time, but they indicate there is at least some CSM. Or if you observe very, 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 very late, and then your features become wide or something like that. Or if you observe bumps in the light curve, usually bumps, magnetars and so on cannot reproduce bumps on their own. So it will be, if you see a bump in the light curve, it will be a bump, a magnetar plus CSM or something that is only CSM the most accurate or the most likely nowadays to be able to reproduce bumps. We don't have anything else that is reproducing bumps like that. So yeah, having a very, very detailed spectral sequence would be the way to go, but we don't have enough observing time to produce such spectral sequences.
Coming back to the host, for superluminous type 1, they are often discovered in low metallicity, blue, low brightness galaxies. What about superluminous type 2? There is a different, it's different, no?
Yes, so I have given this talk a few times, and every time I get the same question. So it's a very on-point question. Yes, so we haven't performed the environmental analysis yet, but it's an analysis that is ongoing. So the results should be out soon-ish, I guess. It's not me performing it, but someone is looking into the host of these things to try to correct
it. In some nearby supernovae, normal supernovae, one can see the progenitor in some or progenitor activity. Do you see any evidence of progenitor activity in the superluminous supernovae?
Yes, some of them show. If you check here, there is this yellow one. I don't know if you really see it.
Mm-hmm.
There is this sort of pre-peak activity, which is reminiscent of what we call precursors. However, this is way more luminous than a precursor, so we don't really know. But since I didn't do like detailed event by event analysis, I cannot say more. But yes, there is this sort of pre-peak bumps that are reminiscent of pre-explosion activity.
So with LSST will be easier?
Yeah, with LSST, we saw, to put everyone in context, because stars have these mass loss events and so on, and we believe that a lot of the powering source of the light curve also can come from CSM and so on. People have started saying, okay, but if a star is doing something before it explodes, then you should see it. And people started looking for pre-explosion outbursts, and they have been finding them, but they are very dim. So it's difficult to know the rates of pre-explosion activity or outbursts because we don't have the depth to really see them all. But maybe the LSST will be the one thing that tells us, no, every star has pre-explosion activity. For that, we also need a big baseline before the explosion happens, right? Yeah, so even LSST starts this year, we will not know the precursors maybe 2 or 3 years from now, because we need the 2 or 3 years baseline to know.
Thank you.
Okay, any other question? If not, then thank you again, Priscilla, for the nice talk. And we end this session of today here. Please, new PhD students, come here so I can mark you. The ones that I know, you can leave.